Hello, today I'd like to talk about the principle of the magnetic compass. The magnetic compass is a very old navigation tool. It has been used for many forms of the navigation. You could remember when you were a scout, so the teacher will teach you how to use the compass, the magnetic compass. Is very easy and it's very simple, as you can see on your left. Um, But the magnetic compass that has been used on the vessel is totally different. And every ship and every vessel supposed to and have to install the magnetic compass according to the SOLAS. So it's already defined on your slide, the chapter 5, regulation 19. It doesn't matter what size of the ship, you're supposed to have the standard, well adjusted, properly magnetic compass, or the other mean that would help you to tell where you are on the earth and how do you go there. So that is very important equipment of the vessel. But the magnetic compass on the vessel is different from the one that you were used when you were scout. As you can see, is a kind of pole, and there's a small ball, on the both sides of them. We call it the binnacle. The binnacle is the same concept of the scout compass, but they have more equipment to help you to correct the error that will came across later. So before we understand the magnetic compass, we need to understand what is called magnetism. The magnetism is described about the magnet behavior of the earth and the magnet behavior in nature. In common sense, that you can already know that the north pole of the earth is supposed to be in the north and the south pole of the earth is supposed to be in the south. To be more precise, that the north pole is somewhere in the Greenland, above Iceland, above, far, far above of that continent. But if you're talking about the South Pole, it is roughly under New Zealand. We could call that area as the Antarctica. So the North and the South, in you understand, we call it the geographic North Pole or geographic South Pole. But the magnetic North Pole and the magnetic South Pole is different because, as you can, well, you may have known before when you were a scout, that if you have a look at your compass and the needle, which is represented by the red color, is always point north. It's always point north. The arrow that point is exactly the area of the geographic North Pole, which is above Iceland in the Greenland. And again, the other side of the needle is gonna point to the geographic South Pole, which is Antarctica, underneath New Zealand. But the fact is the actual force of magnet in the North Pole is not the magnetic north, but it is the magnetic South Pole. It's totally different. And again, in the south, the force of the magnet that force your compass is the magnetic north, the magnetic north. But again, for everybody to understand exactly the same way, for navigation, we call the magnet at the geographic North Pole, we call it the magnetic North Pole. And again, we call the the influence of the magnet at the geographic south pole, we call it the magnetic south pole. So um, you don't have to confuse because it do not because you could remember you could understand like the North Pole is on the north above Iceland, and somewhere around that area we have both. We have geographic North Pole, which is the point on the location, and also we have another point we call the magnetic North Pole, which is the point where the power or the influence of the magnet is is there. And why is that? Because of the basic concept of the magnetism is the like poles repel each other and the alike poles attract each other. So that means if you put south against the south, so the both of the magnet will be pushed away. On the other hand, if you put the south against the north, the magnet two two of them will be bring close together. But in terms of the magnetic compass, there's something different because there's some effect and influence that can make your compass point to the different direction from your destination. The first is we call it the declination of variation. It happens when you're traveling through the earth in different locations. You know, in different locations, that means the force on the line of the magnetic line of force is different, and that means your compass will be directed according to. For example, if you move close to the magnetic north pole or magnetic south pole, so your compass is pointing to that pole very fast and very strong. So we call it declination and variation. The other thing is if you have your compass on your hand and you have somebody else have the kind of the magnet on their hand and they walk by you, close to you. So because of the magnetic compass effect on the magnet, on the magnetism, so that's mean when that people with the magnet walk by you, walk past you, so your magnetic compass will point to that guy, because it's follow the magnet that closer to it. So that caused the error. You can miss your destination, you miss your target and miss course and off the course. So that is the idea. So we have a look closer to the magnet and we see on the picture on your left, so there's a lot of arrow around. And you could have a look carefully and you can see the north is represented by red color. And all the arrow will go out from it. So that arrow is represent the magnetic line of force. And if you have a look at the south, which is blue color, you can see all the arrow will come to the south. So we can understand and remember that the north, the magnetic line always go out, and the south, the magnetic line always go in. So it's gonna help you to understand the behavior of the needle under the influence of the magnetic line of force. But if you have a look closely to the pole, which is the both end of the magnet, it looks like it's like a center of something because of all the arrow. If you have a look closely to the south, all the arrow will come to the same point. And if you look at the north, it's always see like the arrow is going out from the same origin, same starting point. So that's represent the strength, how strong of the magnetic force. So that means the magnetic force has the strongest properties at the pole. So if you closer to the pole, so your compass will under the very strong influence of the magnetic line of force. But if you move away from the pole, for example, like this picture, if you move to the middle of the magnet, so you can see the arrow is not sort of high density compared to the pole. So that means your compass will have smaller effect in that area. So that is the reason that why the magnetic compass have some error that called the declination or the variation. So in the real maritime navigation, so they're gonna have some kind of the table, some kind of the information for you. For example, like if you're in the northern hemisphere and with some altitude, some latitude and longitude, so they're gonna show you that what types of the declination is gonna be. It's gonna be heading into the west, further to the west or further to the east. So that's something like that. But you would understand if you move closer to the pole, so your magnetic compass will behave strongly to the pole. Rather, easy to point to that pole. So we already know that a lot of line of the magnetic line of force is in the pole, but how do we count it? How do we count it? Count it as the number of line. How do we define? So we define it, the magnetic line of force, we can define it as the field flux. It's represented by the theta, and the unit we call is the Weber. But it doesn't matter because it's a way for you to understand and comprehend how much of the magnetic line of force is going to be. But the next interesting is the force. So you could imagine if we have two different magnets, and if the magnet number 1 is larger than the magnet number 2, so we could imagine that the magnetic strength of the magnet number 1 should be higher than the magnet number 2. So if you put the same pole closing together, so they're gonna repel. It's gonna push away. So that means the magnet number 2 will go away further than the magnet number 1 because the magnet number 1 is larger. So that kind of strength is change the force between two magnets. So we can calculate it by timing the strength of the first magnet times with the strength of the second magnet and divided by 4 pi r squared. R is represent the distance between two magnets. So if two magnets getting closer and closer, the force that's going to attract or repel will be larger and larger. So that's the idea. So that's why we have to be careful when we navigate the vessel close to the pole, because of the magnetic compass will point to the pole directly or maybe repel from the pole. It's very easy and we make it error. So the next, if we have the kind of needle that is made by metal or steel, which is behave under the influence of the magnet, and we put the pole into at the middle like in the picture, and we move the magnet around it. So it happens like this. If we're moving the magnet around the needle, so the needle can rotate. It can rotate. If they have the same pole against the magnet, so they can repel. So it's gonna rotate away from the magnet. And again, if the different pole come closer, so it's gonna rotate closer to the magnet. So it's kind of make it rotating. So we call this the rotation because of the magnet. We call it the magnetic moment of the magnet. It's too many magnets. But the idea is you need to have the strength of the magnet. According to this picture, this strength of this guy. If they have more strength, that means it can rotate the needle very fast. But they have smaller magnets, so it can rotate it very slowly. So that's the idea. So we need that strength, and if this needle is longer, so the ability to rotate is much larger. You know, if you could imagine if the one is 2 times longer than the original, and you use the magnet into that end, it's gonna rotate. It's gonna rotate easier. So we came across with the formula that the strength times the length. So the length or the represented by L is represent the distance between the pole of the needle. So that is the concept. So now you could understand that if you replace the pole by the water and you float that needle onto the water, so it becomes the magnet. It becomes the magnetic compass right away. Okay, next now we already know that if we fix the needle in the middle of it and we move the magnet around, so you can make it rotate. And you already know that um, if you put the magnet closer to the needle, so the needle will rotate much more quicker than than when when you move the magnet a little bit far away from the needle. Now we have to so the needle, the rotating needle, can tell how strong or what kind of the strength of the magnetic field is gonna look like. So that's why we have a concept of how do we calculate or determine the field strength of the magnet or magnetic field. At the moment, we don't uh, seriously care about the Earth magnetic field or the magnet from the normal magnet, but we consider only the how the needle behave or rotate under the influence of the magnet. So have the we have to introduce the new parameter. We call it the field strength. We use the capital H to represent the field strength, and that strength is gonna change depends on the distance. If the magnet is far away from the needle, of course the strength should be small or less. On the other hand, if you put the magnet close to the needle, so the needle will do something about it because of the influence of the magnet. And because of the distance is so close, so the force, the strength that acting upon the needle will become more powerful. And we introduce the first case, we call it the short magnet, is when we decide which magnet is short or long, it really depends on if the length of the magnet is smaller than the distance between the magnet and the needle. We consider that case is the short magnet. Again, if the length of the magnet is smaller than the distance between the magnet and the needle, we consider that case the short magnet, which is Most of the time, we consider that case the short magnet. And now we have to consider about the, the position of the magnet that acting upon the needle. We have a several, if you could draw something, and we could we could have a magnet, and we could have a needle. So we can put magnet anywhere we like. We can put it on top, left side, right side, on the bottom. It doesn't mean anything. You can put it in the north position, the east position, the south position, or the west position. It doesn't matter. But which position have the influence better than the others? So now we call the position of in this case, if we have the needle here and we have the magnet right here in the same line, so we call this situation is end on. We call it end on. So the position is like that. And the strength we could calculate from by the formula at H equal to 2m divided by d power by 3 times 10 power by 6 over 16 amp per meters. So that is the formula from that position. So it doesn't matter, it can be here or here. So these two positions we call the end on position. So now it depends on the distance, isn't it? It depends on this guy. If the distance is increased, of course the strength will be smaller. But the next case, we call it the broadside. What it look like? It look like this. Is if we have the needle again, and we have the magnet. Yeah. The magnet is on the sideway, is sideways. So we call that position is the broadside. Again, it can be here, right in the middle of the needle, or here, which is a little bit of angle, and here is a little bit of angle as well. We also call this situation is the broadside position because at the end of the day, you're gonna get the angle. Follow that. So we could calculate anyway. But the simple formula to calculate is we consider only the case that the magnet is in the sideway, exactly in the middle of the needle, but on the sideway. So we call the broad sides. So this formula H equal m over d power by 3 times 10 power by 6 divided by 16 is belong to the broadside, which is this case. So, so that is how to calculate the strength. So the next, now we already know that different position, either end on or broadside give you the idea what kind of thing. But if you go back again, so you can have a look, you can notice that is very important as well. The strength of the end on position is 2 times larger than the broadside position. Okay, so that is gives you some idea how which position had more force or influence on the needle. And another tip about how to calculate the field strength, you can use them just in case if you know the flux. If you know the flux, basically by the experiment, or well, some cases you have a table with you, a paper or document with you, so you could calculate it by using this formula. But again, the main thing is distance. Is distance. It depends on the distance. It doesn't, so each position have specific strength. All right. So now so that's mean if we have if we point out is the needle, this is the needle, and this is the magnet. Okay, so what position is that at the moment? Is, of course, is the broadside. Is the broadside position. So now we have the broadside position, but take a look at this. If we have if this line is represent the magnetic line of force, which is exactly the same with this one, because you already know that the north, the line of force always go out. And the south, the line of force always go in. So it's obvious, exactly the same. So you could imagine if you put the needle right at the middle, but in sideway with the magnet. So the blue color of the needle will point at the red. No, it will in line as the red of the magnet. The blue here and the red is here. On the other hand, the red of the needle also look at the same way as the blue of the magnet. Okay, I clear it a little bit. So when you move the needle up, which means the needle will move closer to the pole, which is the north pole of the magnet. So if you move up and up and up, so your compass or your needle will be rotated. Your blue color will rotate and give you an angle. And if you move up and up, so your compass will rotate. Your blue color will be at the end is now is horizontal. It's horizontal already. On the other hand, if you move your compass or your needle down to the blue section of the magnet, your red section will be tilted, will be rotated and give you an angle as well. So in this case, if you could imagine, if you if if you have a ship, if your needle is on your vessel and your vessel is going up, and your vessel is going up that way. So that means as long as your ship is heading to this course, your magnet compass will rotate, will change, will give you some angle, which is make the destination angle compared with the needle angle is going to be more different as long as your ship keep moving up, moving. So the idea now you already know that different, because I told you before, different location, different strength, but ultimately different location your compass or your needle will rotate, or we call it the deflect, will deflect it different angle, different places, different angle. That means your previous position, if you count it out, maybe some angle is going to change if you keep moving to that, if you keep moving into the same course, so it's going to change. So, and this is to point out that the deflection of the angle is increased as the needle moves close to each pole of the big magnet. But again, it happens when you use the magnetic compass for your maritime navigation. How about if we have another magnet? In this case, what this guy do? What this needle do? Because now this little needle is under the influence of magnet B, and the magnet A. So what is going to happen with the needle? Well, does this needle have the pole, that allow this needle to rotate? I don't know. At the moment, we don't know which way. Is it going to rotate clockwise? Is it going to rotate counterclockwise? Is it going to rotate in east or west? We don't know yet. But right now, we have at least two line of force. One is belong to the magnet A, and the other is belong to the magnet B. So what we gonna do about it? We need to get the angle. We need to get the angle, or in this case, we call it the tan deflection. This angle is not permanent. This angle can change. Can change. Depends on what? Depends on the distance. Depend on the distance of between the magnet A, and depending on the distance from the magnet B, and moreover about that, it depends on the strength, how powerful of the magnet A. If this magnet A is larger than the magnet B, probably this magnet A have more magnetic force than the magnet B. So which means your needle is rather follow the magnet A, something like that. But before we going that, we need to know, because the magnet is inseparable inseparable. What does it mean? It means it always have two poles. It always have two poles, north and south. Always have. So that means if we consider the moment is equal to the strength time length, as we already know. But in the case of the magnet, because they have north and south, so that means if your needle, for example, like this is the north and this is south is your needle, and this guy is the magnet. So what is going to happen? So that means the north will follow to south, and the south will follow to the north. Something like that. But okay, I clear the picture again. If okay, and we have something stick to it. So that means if this one is going to repel by this one is going to that way, and this one is supposed to go to that way, right? But not quite, but not like this, not like this, because if you put into because it is the magnet, so that means the north act on the north side of the needle and also act on the south side of the needle as well. In the meantime, the south also act on the north and the south is act on the south in the meantime. So they have a couple. So they have the problem with the couple. If I put it again here, north and south, and we put south and north. So now you know it's going to become like this. But and again, but the south also acts to the needle in the both way. So we call it the couple. We call it the restoring couple. So have a look into this guy. So if we have a point, it's called a pivot point, a point that we can rotate, and right in the middle of the needle. So the length is going to be half from the center to the north and the other half from the center to the south. So the moment that happened here, and if we put the needle under the field, under the magnetic field strength of the magnet, so the force that make that needle rotate is one is act on the north and the other act on the south. So we call it the couple moment. So we can calculate it as the H, which is the strength, and M is the pole strength of this. Okay, M is the pole strength of this, which is equal. So it means the couple moment is you could use this one as well. Is H M divided by 2 plus Sm divided by 2. So it's a couple moment. And that is the case that the needle is lie in the perpendicular with the field strength. But if your needle is in the angle like this, so the couple moment will be H times M. H is the field strength, M is the strength of the pole, times sine theta, time theta. Because this is the force, that is the strength, and that is your L, that is length. So what is the length is? A chord is the length that you can calculate by half sine theta, and because it's a couple, so you time with 2, so you can have this is a couple moment. So only the needle under the influence of the magnet behave like that, which bring us to this page. So now we have the situation that the first magnet is the Earth magnet, which is string of H, and we have another magnet. We have a string of F acting on the needle. So the moment that make the needle rotate under the influence of Earth magnetic field will be Hm in sine theta. M is the strength of the needle. We use the subscript n, call it the needle. And the other is the moment that make the needle rotate according to the external magnetic field is had F mn cos theta. So we're finding the ratio between this, and we can have the tan deflection or tan angle. Again, if you change the position of the external magnet into that, so we have the same situation in case of the magnet, but for the external magnetic is different because now your force is like this. Your force is like this. So that means under the influence of external magnet, the force is exactly 90 degrees with the length. So now there's the idea of the Fmn sine 90. And we're finding the ratio between the influence of external magnet and the influence of the Earth magnet, and we also have a sine theta, and that is the deflection angle. That is the deflection angle. But it came from the different way. Depends on the position of the external magnetic field. So now you can roughly guess, and you could calculate a little bit about it, And this would help you when you have to do some magnetic compass correction, which is gonna tell you in the next chapter. We're gonna continue from the last time about magnetism, because we're already learning about how to deflect, how to make the magnet or the compass needle to rotate. It really depends on what kind of the external force that react to the needle. If you have the bar magnet, which is you put the end against the needle, so we call it is an end on. It's a tip of both sides of the magnet bar. But if you put the side of the magnet bar against the needle, we call it the broadside. So these two effects have exactly the same uh, exactly the same reaction, but the the force, the strong, how strong of each, they're different. Normally, the end on will give you 2 times more powerful than the broadside. But that is the deflection that we put the magnet exactly on the plane, the same plane with the needle. However, because the line of magnetic force, it doesn't occur only only the plane, or what we call the horizontal, which is also affect the needle in vertical direction as well, which is make the needle, when you put the compass on the vessel and the vessel traveling across the latitude or longitude, which mean the different line of the magnetic force, that it gonna have effect on the needle, which is, you could see the needle is shaking. It's like somebody shaking. And the shaking phenomenon we normally call it oscillating or oscillator, which is going to give you some parameter that say, okay, that oscillate or this shaking, how how frequent how frequent of the shaking. So we can call it the frequency, or the other way we could call it time or the period, which is we can see by the formula of this. This is equal to pi times square root of I over h time m second. I is represent the moment of inertia, which is the needle, exactly this, the bar of the metal, and m is the magnetic moment of the magnet. And because it really depends on the magnetic field, the strength of the magnetic field, as I told you before, when we move closer to the pole, which means the force of the magnetic is strong, and of course it's going to have more effect on the oscillating of the needle. So we can come across with the formula like this: t square is equal constant divided by h. H is represent the magnetic field strength. So if you could, well, the more of the strength it is gonna make your compass still, stay still, not moving at all if you move closer. But if you move a little bit farther from the pole, is gonna shake a lot. So you just memorize this about, if you move a little bit closer to the pole, so the your compass is seems to a little bit better in terms of the stability. Stability is much better. But if your vessel is near in the equator, it's going to be a different, because it's far from the pole, from both north end and south end. So that means the influence of the north and south is kind of similar. So this is make your compass a little bit shaky, because they don't know which way to follow. They follow the north either or south, so it's kind of confused, stable. And so that is because of the Earth magnetic field, which is, we already know that the geographic north and the magnetic north is on top of the world basically, and the geographic south and the magnetic south pole is gonna be at the bottom of the world. Okay, and because because we consider the core of the earth, in the middle of the earth, is behave like a bar of magnet. And as you remember, because the North Pole, all the line of the magnetic force will go out, and the South Pole, the line of the magnetic force will come in. And you can see the Earth. The Earth is kind of upside down because of course we already know that the North Pole or the magnetic North Pole, the line of the magnetic force will go in, which means it's not exactly the north, but the magnetic property at the North Pole is the property of the South Pole because the line of the magnetic force will come in. Again, at the south of the Earth or the bottom of the Earth, you can see from the picture at the left show that the line of the magnetic force is going out. So that means we call it the magnetic south, but the magnetic property of it is behave as the north. But again, just to be, it is already understand from all around the world that we keep saying the North Pole is in the bottom, is in the Greenland, in the South Pole is in the bottom, is in the Antarctic, under New Zealand. So that is the key. But that's mean the terrestrial magnetism in this case, the North Pole of the Earth, the line of the magnetic force will come in, and the South Pole, the line of the magnetic force is go out. So that is the key. And you can see the picture in the middle. Well, we have a geographic North Pole and South Pole, and we also have the magnetic North and the magnetic South Pole. So who consider and whose claim that is the line of geographic North Pole and the South Pole? Of course, we refer to the Greenwich, which is in England. So that is the place that everybody, particularly in a maritime society, understand all well. That is the geographic meridian. However, because of the magnetic north and south is a little bit uh, shift or off the line of geographic. As you can see, the magnetic north is going to the left side, which is we could say the westerly of the geographic north, and again the magnetic south pole is shifting at the right, so we could say it's a little bit easterly from the geographic south pole. But again, the line of the magnetic is kind of curved, is a kind of it is semi-circular basically. There's a kind of a curve, uh, start from the south and draw it up to the north. So a little bit of curve. So you could imagine that if you put your vessel with the compass, what is going to happen here? So that means the compass or the needle is going to behave along, they're going to follow the line of the magnetic. So that means if I say we are here, so it looks like the compass is going to stay parallel with the Earth's surface. But if you move a little bit to the north in that area, so you see the line is, well, is going to the ground. Again, the compass always behave exactly the same line of the magnetic force. So that means the compass will, will look down. Will look down. So we call this situation is dipping. And so because of the magnetic Earth line of force has a different location, so it's gonna behave. It's gonna affect the compass in two plane basically.
we can say horizontal plane, we get a variation, is going to rotate east or west, something like that, because of the earth magnetic field, because of the hard iron or soft iron of the ship, and because of the raw material in some places in the earth, which is rather special from the others. That is the horizontal. We call this a variation or declination. And the other is called dip. Dip is say, if you could imagine the compass is like an arrow. If your arrow is pointing down, or if your arrow is pointing up, that means is the dip is happen in your compass. Is look down or look up. And the third one is the total field of strength. As you can see in the picture, there's of the black arrow is represent the angle of magnetic, and the red is the represent the declination or the variation. You know, because if you anywhere in the world, your compass always point to the magnetic north. So if you move, so that means yourself or your vessel is gonna move, but the needle is stay the same, keep pointing the north. But when you are in the vessel and look into your compass, you see a little bit of your compass is rotated, or dip, going up or going down, look up or look down. So we call this situation is the variation for the horizontal plane. But if we have a kind of a look up and look down, we call it a dip as well. And before we go any further, you have to understand first about the angle or the bearing. We have two reference at the moment. We have a geographic north, which is we call true, and we have the magnetic north, which is we call the magnetic. So the angle between this true and magnet, so we call it the variation. And if this variation going to the east, so we use positive sign as the numerical when you calculate for the compass error. So is always positive or plus. On the other hand, west, we always use the negative sign. It's always minus. In case of your compass is stay to the left of the true meridian. So east always plus, west always minus. So that is the key. When when you calculate the compass error. And because of the earth magnetic field has changed over time, that's why we need the table or the equipment. We have for example, like a diurnal, annual, and secular, which is always represent the way to um, how the earth magnetic fields have changed over the time. And the next stop, we're talking about the dip. The dip is the effect of the earth magnetic field in the vertical plane. So it can go for the example, it's looking down. And if you say, okay, this is the north side is looking down, the south side is looking up. So why is happen? It happens because your compass is in the vessel, or or you are holding the compass and traveling along along the earth. So as you can see from the picture at the right, if you are traveling near the equator, so your compass is pretty much parallel to the earth's surface. But you move a little bit closer to the pole, So you are, for example, like this picture, you normally stand 90 degrees on the Earth's surface, but your compass is just look down. It's just tilted down to the floor, which is called is the dip. Why is behave like that? Because of the Earth line of the magnetic always go in the north. So that make your compass keep pointing down, and and that's and we work out the angle. So how far we look down or how far we look up. So we call it the angle of magnet dip, which is represent from the horizontal plane. You could give like the this one is the horizontal plane is like a 0 degree, and everything is going down from the 0 degree is going to be called angle of dip. So the magnetic element that has two elements. First, we have the horizontal force. We normally use the letter H, and we have the vertical force. We normally use a letter Z. Is represent. But before I go further, we need to understand that if the north of the needle point down, which is this area close to the North Pole, we use the positive sign for the angle that we found. And if the south is pointing up, it is a negative sign. So that's that's the thing that you need to understand. When we calculate the compass error, the sign in front of your number is represent which direction that number is represent. Which way, either east or west, up or down. So come back to the horizontal force. So horizontal force, we're looking at the picture on the right. So if your north part is pointing out like this, so we get some angle already. And this angle is referred to the horizontal, which is H, and it also referred to the Z vertical force as well. So your H is would equal to T cos angle of dip in degree. So T is represent the strength or intensity of the force, and the Z is gonna be T sine angle of dip. And I need to remind you again, the dip will be nil, or nil is mean zero near the pole in case of the horizontal force. But in terms of the vertical force, the dip is zero when it's near the magnetic equator and is maximum at the magnetic pole. So this the behavior of two sides of the Earth magnetic line of force. So that's mean different places on Earth have a different effect on your compass. Some and so that's why they produce some kind of the map to help mariner to understand and to realize that which part of the Earth that has very strong magnetic field. So there's a kind of different chart that's produced or published. Um, you can find all of them or some of them in your vessel. So they're kind of different uh, publication. So first we have the table or the map called isogonic. Isogonic is represent the line or is represent the declination, and it's gonna give you the different or we normally say the delta. the value in this isoconic is represent how the different between the true and the earth magnetic. So how the different angle. So that is the purpose of the isoconic map. The other we have an arconic map, which is this one is kind of the draw the line of the earth magnetic line of force from the north to the south, so you can see the whole line. Again, it give you to understand. Well, it's not as easy as an isoconic, but now you can know how you can know the profile of the line of the magnetic. And there's a similar map as is have an isoclinic. So it's a joining points of the Earth's surface. This one is give you a dip and inclination as well. And aclinic, so it's similar to the argonic, I think. So this kind of map, it would help you to calculate the variation and declination and also the angle of dip, and it helps you a lot with the error compass calculation. Isodynamic, again, is the imagery part on the line. It shows the distribution, what does the magnetic line of force of the earth look like. So that is something like that. Some anomaly, something strange about the magnetic can happen all the time. Most of the time is relating to the solar wind. Sometimes the sun, just transfer a lot of energy into the earth, which is make the earth magnetic fields confused, and sometimes make your compass reading in the wrong direction. So we call it a compass error. So that is how the earth magnetic field is going to affect on your compass. It's going to affect on horizontal plane and vertical plane. So so in this page we have give you some idea about because we have the compass. The needle of the compass is that it isn't a magnet. It is not a magnet, but it is a metal or material that can follow the line of the magnetic force. So what kind of material we have? We have a different kind of material. We can have from a metal, gold, copper, plastic, wooden. There are several kinds, but I like to point out that normally we consider most of the material on the ship is the iron and steel, which is we call this kind of material as the ferromagnetism. The ferromagnetism is simply say like in general it's not a magnet, but if they have some energy or some magnetic energy, touch it or make a contact to this kind of material, now they become magnet. But sometimes they can return back to the normal, but sometimes they can also be permanent magnet as well. So that's why we divided the iron on the vessel into two classes. First we call the hard iron. That means when they change themselves into the magnet, they're gonna be the magnet forever. But the other kind of the iron, we call it soft iron. That means once it's turned to become the magnet, give them a time and they can return back to the normal. So we have only the ferromagnetism that happen into the vessel. Apart from that, it really depends. I mean, Well, some leisure like yachts, they made of the fiberglass, which is not there's no much steel compared to the container or the feeder. So it would so the error, the compass error may be smaller effect compared to the large ship. So now we have a look to the actual compass. And well, in this page we see the basic design and the construction of the compass. um, well, it always consists of the needle, but really it depends on what kind of application you use. You can use it as small like a watch as well, or but for the maritime navigation, a little bit of the size is coming into the consideration. First, we have the what we call the dry card compass. The basic concept is have look at the picture on your left. Is represent the right side and is cutting in half, so you can see what's going on inside. So what's going on? We have first we have a steel point. This one is act right the central, the center of the rotation, and you put your needle or magnetic compass, which is this guy. The circle. Sometimes we used to, well, we can call it as a compass rose as well. It indicate the 0, 90 degree, 180, 270, and go back to the 0. And it's also indicate cardinal, north, south, east, west, and intercardinal, north, east, northwest, southwest, and east and southeast. So this one is sitting on the steel point, balanced. There's no up and down. It's going up and down when they came across the line of the magnetic force. But if they sit in the equator, it is gonna be parallel to the Earth's surface. And we have a compass housing. Is not much. It's just a container. But we have the top one. We have a directional dial. Basically, the compass we dealing with two circle. The one inside the needle is always point to the magnetic north, and the outside circle is always, you can work the difference between inside circle and the outside circle, and you can get the course. It is a degree, and the degree dial as well. This one is made. Uh, you need to working out what how much of the bearing, going to the east or into the west. But you have to remember, east is always plus, and west is always minus. You have to subtract when is deviation to the east. No. East is always positive. West is always subtract or negative. You need to subtract when it's deviate to the west. Sorry. Um, so this is just the simple innocent compass. There is a dry card is made by this. Where is the magnetic needle? This is the magnetic needle. This one is just a bearing, just a rotation point. But these guys, this picture we have 8 needle, and all of them have to in line exactly the same line with the line of the magnetic force. So it's a dry compass that's sitting on the air. There's nothing inside, and it's ready to go. And we look carefully inside. This one is very antique. Is this 8 rod is made by steel. It's tiny steel, and you can see there's a lot of string, just string just from the central, and some string is from the needle itself. This string is made by silk, and the rose outside, this one is a compass rose, is made by the papyrus paper, which is very old. But this one is only in the museum that you could see the real thing. Nowadays is very rare. Only probably I think the leisure sailing yacht that would have it, but just for the decoration only. But this design is very close to what we have right now. We call it a liquid card compass. Instead of sitting on the air, so now we use the water. And well, the water that we use is just distilled water, the normal water, but we add a little bit of ethyl alcohol to reduce the viscosity. The whole things about the compass is depends on the central of the rotation. It need to be no friction, no friction. It's going to be frictionless, very smooth, very easy to rotate, easy to go up and down. When the line of the magnetic force change, the needle have to change as well. So it's have to be easy like that. Um, this design is much better than the free compass, because there's a lot of stability. But again, we still have to dealing with the dip as well, because it can going up, it can pointing down and up as well. This one is the basic design that the maritime navigation will design. The next, this is the actual magnetic compass that using right now in the many kind of vessels, all of the vessel. So we call this one is the Binnacle, the Binnacle, and because of the old compass, like dry one and the liquid one, they normally put in the sailing boat, which is made by wood, and that's not much about the metal or steel at all. But because of the modern vessel is made by iron and steel, so there's a lot of compressor going on around. So they need to equip some help basically. Well, first help you can look is these two guys. We call it a soft iron sphere. It's gonna help when your compass showing the wrong direction. What is made of is made by the iron, soft iron, the normal iron. It doesn't behave like the magnet at all. Apart from that, we also have the healing magnet tube. This one also help when your vessel is inclined, not stay up. Just incline, do some angle. So this one is also uh, help to correct the compass when the ship is healing. And there's a two well yeah there's a two window around. We have this one is called the outward ship magnet, and this one is a fore and aft magnet. So the fore and aft magnet is basically is the you put the bar of the magnet, or you put the rod of the magnet inside just to correct the compressor. But the fore and aft is in line with your bow and stern, front of the ship and the rear of the ship. So this binnacle is work. So how do we work with the binnacle? Basically, is in general they already set up. It's already set up when the vessel finish building. So the finished building is mean they adjust everything. Everything is good to go. Everything is seaworthy. the Binnacle also as well. So that means if you working on the vessel and you can see the Binnacle looking like this, so first don't change anything, just leave it like that until your officer asks you to do some correction. So just leave it there, just leave it there. It's okay now, right now, until your supervisor found something and asked you to do something. Then you can put your hands on it, but normally it's okay. And it's not only the binnacle, it also come with the table as well. The table that will tell you which direction, which course of the ship, which direction of the ship it can change. The compass should be should err in some direction. So we're gonna learn in the next part. And you look on top of the binnacle, so you can see again we're dealing with two circles, one inside and the one outside. So we have the inside is represent the needle. Also, we also call this the compass rose as well. It's a kind of the indicator because it's represent, yeah, it's divide the north, south, cardinal, intercardinal. Again, it start from 000 and go back to the 360. And the outer is the is the one that fix. And also, well, you could also dial as well, you could also rotate as well, but this one is the outer circle is belong to the ship basically. So these two line is we call it the rubber line, is supposed to represent your fore and aft of the vessel. So that means you already know that which your ship should be heading into the which direction. We call this one also, we call it a compass bowl. It's kind of bowl, it's put it inside. There's a liquid inside also. It's water plus ethyl alcohol, exactly the same as wet compass. And this one is also inside. There's a liquid, and the needle is floating on that. That is the on top of the binnacle. Again, because we already know that the your needle also can point down and point up, so we call is incline. So that's a meter for you to know how look down of the needle is, how it's look up, how it look down. We call it a clinometer. Clinometer is stick with the binnacle as well, just underneath basically from this picture. But it could give you some idea that how look down or look up of your needle is. Again, when you do the compass correction, we have to dealing with the both plane. First is horizontal plane and the vertical plane. These two with the different situation, with the different material, with the different magnet, or even some kind of a cargo as well. You need to correct both plane, and then you can go, and then you can good to go for the next course. But this one is called the clinometer. So you have two information. First is the bearing, the course information, and the compass clinometer. So that that is what you get from the binnacle. So to to make the correction of the magnetic compass or the binnacle, we have several metals, several magnets, several bar to use. First one we call it the Flinders Bar. The Flinders Bar is a vertical soft iron. Again, soft iron mean it can be magnet, but it can also return back to the normal iron as well. So this is the Flinders Bar. We put it into there's a socket beside the binnacle for you to insert this bar on, and again it will make the correction of your compass, which is we will learn later. So there's a different direction as well. If you look at this picture, so this two is the sphere. You already seen that. This one is the fore and aft corrector. Again, is in line with the fore and aft of the vessel, and the azimuth shift of the collector is the side way of your vessel. But the Flinders bar also we insert this bar in here. But what is gonna happen after you insert that, we will learn it later. So the sphere, there's another name of the sphere we call the quadrantal spheres. This one will help you to correct the magnetic error, the compass error when your vessel is heading to the intercardinal direction, like north, west, southeast, um, north, south, west, something like that. And what you could do about it, we can move it, we can move it to the farther from the binnacle, or move it closer to the binnacle, or even change the angle. We can change the angle as well. But after change, what's going to happen, and how much we can change, and how far we can go, we can study it later. The healing magnets, this one is helping you to dealing with the dip of the compass. So that's inside. There's a container inside the binnacle for you to put the magnet, the bar of the magnet inside, and you put it into the inside, and it's going to correct the vertical axis of the Earth magnetic field. Fore and aft magnet. This one is a tray. It's a kind of tray. There are several sockets. So you can put more than one magnet bar inside. Depends on what the result of your calculation came up. So there's a kind of the place that you could put the magnet bar inside to again to correction, to do the correction of the compressor. And this one is the introduction of how to use the Binnacle. I'm going to show you. Don't mind about this watermark, because I haven't officially downloaded it, and I didn't pay basically. So just have a look. So this is the you can see on top is a compass rose, and this two is the sphere, and that is the Flinders bar pocket. You can put the Flinders bar inside, and and on top, so you can dealing with, again, this ball can dip and up and down. This one is moved very freely, very smooth, no friction at all. And you can see there's a two dial. The one is the needle and one is outside. This is the Flinders bar pocket, and yeah, again this one is in line with the fore and aft of the vessel. So now he going to the size of the binnacle, which is this one is a pocket of yeah, this is the quadrantal spheres. And you can move it closer or further just to correct the compass error. But again, if you have a look this binnacle for the first time, don't touch it, don't do anything, but don't make fuss about it. Just look at the compass rose, and this allow you to move. This this window is belong to this is belong to the healing corrector. Yeah, there's a healing basket inside. So he reached inside, and there's a there's a basket there. You see this basket just ready for you to put the bar of the magnet inside. So you can put it just to correct the vertical error of your magnetic compass. So that is a healing correction basket. So we put this one. We take it out and put the magnet in the basket and then put it back in. So that that is the for healing correction. And yep. So to put it back. This one is the fore and aft correction. See, there's a, well, the one we have seen is a tray, but this one is a kind of slot. You know, you can put it into different. One is belong to the fore and aft, and the other is outward shift. So you can put right that. And again, there's a number on it. You know, 1, 2, 3, 4, 5, 6. The closer to the needle, that means the stronger the effect gonna appear on your compass. But if you insert into the lower number, so that means it's far from your compass, so the effect is gonna be smaller. So if you put it very close, the effect is large, so you can see obvious effect. This is a Flinders bar. So so this one is this pocket can get it out, so you can take it out, and there's already one magnet inside, which is a very huge cylindrical iron. So you can put this into the Flinders bar to correct the compass error. It really depends on how what your deviation calculation will come out. So this can show you that you could adjust the strength of the Flinders bar by using multiples iron, or sometime, you know, if you work out that it doesn't need much more stronger of the magnet, you could put something underneath as well, just to reduce the effect. But it really depends on what your deviation calculation result, which is we're gonna study about how to calculate the compass error in all direction, and how do we correct it. So that is pretty much about yep. So that is the Binnacle. Before we calculate the compass error, we need to go back to understand the basic principle of how to use the magnetic compass. First, we need to know there's a two circle, one inside and one outside. The inside one always point to the magnetic north, and the outside it can dial. You can rotate just to make the course. We have a indicator. It's called the rubber line. The rubber line is like, for example, like this one is the red, is pointing the direction of the chip's head. Where's your head? See the rubber line. And also indication the fore and aft line of the ship, what is front and back. And it's also, inside your compass bowl as well. So that is critical thing that you need to look at. Where you want to go, it depends on where's the rubber line point. And we have a different reference. So you have a look into this picture. This picture is represented ship. And again, the rubber line is point to the fore. And what we have reference, we have a geographic north, which is we call it true. And we have the magnetic north, sometimes we call the magnet. And we also have compass course. We have 3 courses. One is the true course. Second one is the magnetic course. And the third one is the compass course. So which one you follow? So which one you follow? First, we understand the angle between the compass and the direction of the ship is the compass course. And the direction of the ship relative to the compass north, for example, like this picture, this arrow is pointing to the west of the ship. So that means whatever which direction here. So the ship is, so your compass is westerly from the ship head. The indication positive of the rubber line relative to the compass card. So what about the magnetic course? The magnetic course is the angle between the magnetic and the direction of the ship head. This is magnetic. This is magnetic. So the direction of the ship is related to the magnetic north. So the magnetic north. And the difference between the magnetic course and corresponding compass is the deviation. This one and this one show different. That means there's a deviation going on. How about the true course? The true course is the angle between the geographic and the ship's head. The direction is relating to the true north. And the difference between the true course and corresponding magnetic course is the variation. It's a variation. We have 2 things. So that means in this picture, the compass is showing an error, right? Because of the magnetic is here. Your compass supposed to point to the magnetic here, but is slightly west from the magnetic. So now it's error. How do we know that? What we need to know from this. We need to know the different angle from here. We need to know the different angle from the magnetic and the compass. So who got this different? There's a table to tell, because it really depends on the head of the ship. This one is heading into roughly east, so that means your compass is westerly error. So that's going to tell something. But you need to know that there's a three courses. True course, the head of the ship compared to the true magnetic course is the head of the ship compared to the magnetic pole, and the compass course is the head of the ship compared to the compass. What is the arrow point? So we have a look into the example. We have our vessel, and we have 3 floating objects surrounding us. How do we say where it is? If you're not trained, so you probably say, okay, if you could fly, and look down, and you can see this object is on your right, and this object is on your left, and this object is on your left side. But that's okay if you could fly above the ship, and you can say, everybody understand, except everybody in the ship. You can tell everybody, but people inside the ship don't know exactly the same as you do. Where do I have to look at? But easy for you because you fly above, so you can see everything. You can point to everything. So that's come across with the relative bearing. We have two circles. One, the blue one is represent the compass, and the red one is represent the ship. Now is exactly the same. 000, 090, 180, 270. Go back. It's again the same. So how do we tell the people inside the ship to look at the object? How do we tell? So what do we do is we use the kind of a formula is relative plus chip heading into equal true bearing to object in chart. So if this is the chart, some kind of electronics chart, something like that. So how do we call this object? It's going to be you are at your east 090 of your vessel, right? It's 090 of your vessel. So what's the people inside the vessel gonna do? They're gonna have a look into the compass, which is in the Monkey Island, or you can have the relay compass inside the ship as well. And you turn and you look at where is 090 point. So you go into that way, so you can see the object. How about the two guys on the left? So the one on the top left is probably 280. Again, you can have a look into your compass in the vessel, and then you see where 280 point. You can run to that place, and then you can see the object. So this is the reference is difficult to find when you are on the open sea. All you need to rely on is the compass, gyro compass, GPS, the electronic equipments that could tell you. But sometimes, and most of the time, your equipment can lie to you. Sometimes it's not true. You have to be careful. You have to compare with the different equipment before you determine the actual course of your vessel. Don't rely on one equipment. Just have a look around. Everything is coming to close to your hand, and everything is got an error. So that means you need to be careful. You need to be sure every time that before you say anything about the course of the vessel, you need to make sure that you compare with everything. You make the risk as small as possible before you move forward. And again, it's talking about the dead reckoning, the DR in chart. So for this example, as 0700, so your vessel is in the star point. So what's going to happen at 7:45? 7:45. So this one is a nautical chart. This one is a compass rose. So you can have so this is a trajectory of the ship course, and we don't know. We have no idea. So we just mark some point. Let's call it 7:45. This point is called the unknown position, but this point is called the dead reckoning, the DR, the last known position. In general, we normally the ship would take course for 45 or 1 hour, and then we check the course again. So that is the same thing. And what tools that help us to know the course? So we have the compass rose, and we use the ruler and tap to the compass rose so we can have it true course. Which this one is 145, 135, 135, and the speed of the vessel is 5 knots. So the speed is not going to change. So where at the 745? So we start with the 745 minus 700. It's going to have 45 minutes. So we convert the minutes into the decimal by divided by 60. It's going to be 0.75. And you times with the speed. So it's going to be 3.75 nautical mile. So that means you can draw the line and you can mark is the 3.75 nautical miles. So you can see that is the where your vessel is going to appear at 7:45. So the DR is the dead reckoning, the known position, the last known position we call it the DR. Sometimes we use the abbreviation like the DR position. And what about if something wrong? If something wrong, if when the 7:45 come and you check your GPS, so you are here, you're off the target, you're off the target, you're off your expect destination. What happened? So it's simple. It's happened because of the current of the sea. So the direction of the current we call is set, and it's not only the direction of the current, also the speed of the current as well. We call drift. So that means with 5 knots in 135 direction, but because of the current, so that make your ship off course. So how we gonna do that? So we put the position in the chart, and then we work out the point that your vessel is supposed to be. So we have a so that is your location, and you draw the line into your expecting position, and you can use your ruler, use your divider with the same angle, and put it into the compass rose. So you know it's about 220. So 220 is the direction of your current. How about the drift? So again, it's supposed to be 3.45, no, 3.75 miles. So that is off a little bit. So it's not 3.75. So you use divider making the distance of the chart. So for example, if you make the distance from the divider, so it found out is 6 mile, 0.6 mile. So the drift, the speed of the current is going to be 0.6 times 0.75 is equal to 0.8 knots. So now you can have the direction and the current speed. So that is the chart, and you working with the chart with GPS, with gyro compass. Ethics is a good practice nowadays. So the idea is you know your dead reckoning position, and then you're working by the point the true course, the exactly true course, and working out the speed. And if you find the current, so you find the direction, You find the drift, and you can um, know what's going on with your course.